All right, so here we are, class number 8. What did we get to in the semester? I think it's 30, right? Hard to believe we're already almost a third of the way through the semester. So we're continuing our discussion of precipitation today, and we're going to begin by playing around on the web to try and identify sources of precipitation data and nice statistically computed summaries, and then everything all the way towards the raw data itself at an individual station. So before we begin that, any questions related to the concepts from last class? Well, let me ask you a brief refresher question. If we had a quiz today, which we're not, but if we had a quiz today and one of the concept questions was, what causes rainfall? What would you say? What causes rainfall? What'd you say? Air? Okay. So air goes up higher, all right, and then when an air parcel goes up higher, what happens to it? The pressure goes down, which forces it to cool. All right, and so cooling air has what effect on relative humidity? It increases the relative humidity. So it decreases the solubility of water in air, which means that some certain mass of moisture that was in the air, that doesn't change, the mass of H2O particles. But since the solubility decreases at cooler temperatures, then that means that on a relative basis, the humidity is higher. So it's getting closer and closer to full saturation. And then when it reaches saturation, that water's got to go somewhere. It can't be dissolved in the air anymore, and so it begins to condense on dust particles and other nucleation sites. And they bounce around in the atmosphere until they get large enough that then they begin to fall. What are the 3 things that forces air to rise? 3 different reasons for lifting that we talked about. Can you remember 1 or 2 or 3 of those? All right, so frontal lifting, right, when high and low pressure or cool and warm air collide, and that forces the warm air up over the cooler, more dense air. All right, so that's one, frontal lifting. What's the other one?
Physical obstacle.
Okay, a physical obstacle. What's the official name for that? Starts with an O. Good, good. We're headed in the right direction. You've narrowed it down. There's 26 letters in the alphabet, right? So far, so good. What's the next letter? Orographic lifting. Orography. So that's the idea of Hawaii, you know, the windward side versus the leeward side. And then the last example has to do with the heating of the ground surface. Convection. So that's convective lifting. All right. Well, it's good we didn't have the quiz today, isn't it? We will have a quiz on Monday, though. No, wait. We don't meet Monday, so we won't have a quiz Monday. We'll have the quiz on the day of the homework. We'll have a quiz on Thursday. All right. So here's the data. Let's begin by PRISM. So type into your browser prism.oregonstate.edu. Let's take a look at what they've got for us. It's these really nice maps that not only show climate averages for precipitation, but then also totals of recent, of recent data on a nationwide basis. So if you click on normals and scroll down, this is on an annual basis how much precipitation you can expect at different parts of the country. And so this is a great summary map just to get an idea of not only how much precipitation a region has, but also because of that you can get an idea of what kind of crops are supported. And so for instance, in the West, Nevada, Arizona, Utah, Colorado, New Mexico, it's not the breadbasket of the United States. I mean, they do grow crops there, but they all have to be irrigated from mountain dams. And in contrast, in the Midwest, where we've got persistent crops of wheat, corn, soybeans, that's all because there's sufficient precipitation on an average annual basis to support the crops without irrigation. So it's kind of interesting to look at the highest precipitation in the continental United States is actually on the coast, Washington and Oregon. It rains a lot there, and so it's got those well-earned reputations. We also get quite a bit of precipitation. Now, if we think about West Virginia, anyone want to speculate why we've got this different color in this range compared to everywhere else, which is this more aqua band instead of a deeper blue? It's the mountains, yeah. So it's where the elevation is higher. So we could pretty confidently speculate that this additional precipitation that they see in the eastern part of the state is due to orography. So there's that precipitation didn't happen in the other locations because the air wasn't being lifted up to higher elevations. All right. So that's just the normals, but what's kind of interesting is to look at, we can see what's happening this month. Where do you think we're going to see a lot of rainfall for this month? We scroll down. Yeah, Florida has been getting a fair amount of rainfall. This is precipitation just in the month. So I think, let's see if we look at the date range of this, September 1st to September 13th, 12 inches. It's pretty much purple through a lot of this. I think there are regions that have 16 to 20 inches of precipitation, even a few faint areas where it looks like it's more than 20 inches. Now, if you think back to the normals, let's go back to the normals for West Virginia. We didn't actually look at the absolute amounts there. So West Virginia is in this range of 40 to 50 inches per year. And so what we're saying is that in Florida, since the 1st of September, they've had 20 inches of precipitation, so half of our annual average precipitation amount just in less than 2 weeks. So that's obviously a spectacular amount of precipitation. It's been very wet there. You know, things have been kind of wet here in West Virginia, but not nearly to the scale that they've had in Florida. Now, Texas, on the other hand, I think that hurricane was before September 1st, right? So we would have to, let's see, we couldn't do the month to date. I don't know if we can go back to prior 6 months and find it. Okay, so August 2017, and there we go. Now we pick up a lot of precipitation in the Houston area. So Houston's on the sort of the coast towards the east of Texas. So the effect of the hurricane is definitely visible there for the period ending 31st of August. So PRISM is pretty cool. The way that this data is put together is they use a variety of input sources. They use stations where they're available. And you can download the data in a grid system so that even if you're interested in the precipitation in a spot that's between gauges, they have a mesh for the entire United States that on a day-by-day basis, they've estimated what the precipitation was in that location. All right, so that's the first of the 3 sites we're going to look at. Now the next one, that's kind of just either for research purposes or for curiosity purposes. You know, from the standpoint of engineering design, you probably wouldn't go to PRISM. But for engineering design, you would definitely go to this Precipitation Frequency Data Server. That's what PFDS stands for, Precipitation Frequency Data Server. So now click on that, and we've got a map of the United States, and we'll click on West Virginia. And what it does is it brings up a zoomed-in map of West Virginia with this red crosshairs on it. And you could type in the latitude and longitude of a location that you're interested in and submit, and it will automatically snap the crosshairs to that spot. Or you can just drag them. And so we'll zoom in a little bit further. Okay, here we go. Plus, zoom in a little bit more, and let's drag this down towards the Huntington area. Let's put it right on the building that we're located. Okay, so here, about 3rd Avenue, before the bridge. It's not, we don't have to zoom in. It's not going to change a lot from one city street to the next. But when you've identified a location, let's look at these options across the top here. First of all, you can either have it choose and report on the table either precipitation depth or intensity. Let's start with depth. The units available, English, so it's going to have units of inches if we leave it on English. Now, this time series type, partial duration versus annual maximum. And this is a decision where for partial duration, you could have 2 really big storms in a year, and you could include both of the storms in the statistics, or annual maximum is that you, looking back into the historical data, you would have only included the largest storm for each individual year. It's a little bit simpler to calculate the intensity, duration, frequency table if you're using annual maximum and you're doing all of that manually. But partial duration, I think, is accepted as the more accurate approach. So we're just going to leave this on partial duration. So we've identified the location, it's English units, precipitation depth, and now if you scroll down, here's a table that is telling us the precipitation depth for a storm with a certain return period. So you can see here it says the average recurrence interval, and then a duration. So let's look at, for a 2-year storm, the 5-minute storm depth is going to be 0.422 inches. Now, if the storm lasts 10 minutes, then it would be 0.659 inches. If the storm lasts 15 minutes, then the depth is going to be increasing for all of these. When we look at the intensity in just a moment, you'll notice that the intensities are highest for the short duration and decrease for the longer duration. But this is depth, which is intensity times time. And that's why as you go down along a certain row, the amounts are continually increasing, is because the storm duration went up, even though the intensity is lower for any one of those rows. All right. Now, here inside of the parentheses are the 90% confidence intervals. And remember that this is all statistically extrapolated, partly because we don't have a rain gauge right in this location. The data that it's getting is being extrapolated from the Huntington Airport, and there's, I think, a station in Gallipolis, and there might be a state. We're going to look at the actual stations in the area in just a moment. But number one, it's spatially extrapolated and averaged. And then the other thing is that we may not have a full 100 years worth of data for each of these locations, and so they're going through a process of estimating. If you have 50 years of data, you're going to have to estimate what the 100-year storm would be like if you only have 50 years of observation. And so they know, based on previous studies in locations where lots of data is available, they know when you make that extrapolation how much error is introduced. And so if you want to be 90% confident that you're designing for the right precipitation depth, what you could do in a worst-case conservative scenario is use the upper range. So you can be 90% sure that the precipitation depth for a 2-year, 10-minute storm is between 0.606 inches and 0.722 inches. So there's a 10% risk that actually the 2-year, 10-minute storm is either above that or below that. So if you're designing something with a really low risk of failure, it's not going to put lives or property at risk if it fails, like the culvert at the bottom of somebody's driveway, you wouldn't necessarily use this upper value. But if you wanted to be 90% sure that the system is going to survive a 25-year storm, then you'd use the upper value inside of that range rather than the middle value. All right, so these are all precipitation depths. Now, if you're following along here, change it from depth to intensity, and automatically the table is going to reformat itself. And what you'll notice now is that these bold values, instead of getting progressively larger, are getting progressively smaller as you work down through the table. So from top to bottom, what it means is the intensity for a 5-minute storm duration is going to be a lot higher than the intensity for a storm duration that lasts a full 24 hours. So all we've done to switch between the two tables is we divided the amount by the duration to get these intensities. But the same trend is visible if we work from column to column. As the return period increases, so does both the intensity and the depth. So a 100-year storm has higher amounts than a 10-year storm. And a 10-year storm has higher amounts than a 2-year storm. What's the percent chance that we'll have a 2-year storm during 2017? It's a 50% chance that we'll have a 2-year storm this year. What's the percent chance that we'll have a 10-year storm during 2017? 10%. So all of those percentages are cumulative. So there is a 20% chance of a 5-year storm and a 10% chance of a 10-year storm and a 4% chance of a 25-year storm and a 2% chance of a 50-year storm, and so on and so on. And towards the end of the semester, when we look at flood risk, we're actually going to integrate that risk profile to find out the total damage you can expect in any given year, because you may have $1 million worth of damage when there's a 25-year storm, and there may be $3 million worth of damage if there's a 100-year storm. And so in any given year, there is a risk of all of those events happening. And so we have to have the piece, the annual piece of each one of those events when we try and spread the risk. Instead of being in just one isolated event, we would rather pay insurance and kind of, it's better to pay $100 a month for car insurance, for instance, than suffer the entire catastrophic loss all at once. So flood insurance kind of works the same way, and we have to look at these probabilities of a certain storm happening in any given year. Okay, so this is a really useful tool because let's say that you're doing a project when you graduate and you're going to be out in the middle of nowhere, West Virginia, and there's no rain stations there, and you have no idea what the precipitation is going to be. What you can do is you can identify the location and then automatically get your IDF table. And in fact, here's in tabular form. You can also have it format a figure, graphical. So there it is as that IDF curve. It's a logarithmic scale both on the horizontal and on the vertical axis. So it's very useful. All right. So the last thing we're going to take a look at is where you get the raw data that these two tools are based on. So let's click on this final, you can't click on it, you have to type it in. So www.ncdcnoaa.gov cdo-web. I was working on this earlier just to refamiliarize myself with where things are. It seems like every time I come to this website, they've reformatted it and all the buttons are in different places and they've all been renamed, and so I have to remind myself every year. When I was doing it earlier, it wasn't working with Firefox. It wasn't working right. So it would be better if you use Chrome or Edge, heaven forbid. Use a Microsoft browser. All right, I think that's the default one on here. So click on that. Let's see what happens. All right, so what we're going to do is use the data tools. Is everybody at this page? Climate Data Online. All right, so click on Data Tools and then find a station. We want to get the data from an individual station. And you can type in a search location, so let's type in Huntington. Let's see what is in the area. And it zooms in a little too closely on Huntington. We'll zoom out a bit. But before we get to see the data is the data we're interested in, we have to identify a category and a date range. And so I'm most interested in precipitation, so I'm going to click that. And then here for the date range, let's say that I'm interested in, just generally speaking, data from 2000 until now. So I'm going to click September 1st, 2000, and then the end date is the most recent date that it has the data for, which is Monday, and then apply. And then it's going to bring up stations that have precipitation data during that period. You can see that most of the stations are clustered around the urban area here, Huntington, Barbersville, and so on. There's one down here at the airport, though. Click on that. It gives you a quick summary of the data that's available there. It's saying that that period of record for the airport is from 1961 till 2017. It has 100% coverage. The coverage means if we click on another site, it won't have 100% coverage. 96% is unusually good. Sometimes the instruments that they have are offline because maybe the batteries ran out or the data logger's full, or there's a lot of different reasons why you can have less than 100% coverage. Sometimes it's just a funding issue. The government sometimes goes through cutbacks, and for a few years, gauges will be offline during an entire a big block of time. A gauge will be offline, and then they'll bring it back online when funding is restored, which is kind of a pity because the data is really precious, and you hate to see it go uncollected. But let's download the data for the Huntington Airport. So click again here on Huntington Airport and then add to cart. Unfortunately, the way that the system works is you have to create an order for the data. You can't just click on it and immediately download it. Their server has to process the data and put together an archive for you that then, after a few moments, then you're able to download. Let's see if we can crash the server by all downloading Huntington at the same time. We'll do a little quick denial of service attack here. Click on Add to Cart. We can specify the exact dates when we check out. This was just kind of a preliminary date range that we're interested in. If we view the items in the cart, we are going to want to download it as CSV. That's the one that's most easily opened in Excel. You could also do the text file. That's fine as well. What we definitely don't want, though, is the PDF. The PDF is not machine readable in the same way that the text data would be. If you were going to do a lawsuit, there's a way of certifying the accuracy of this PDF. So I think this is more what a lawyer would want to download if you wanted to know the exact precipitation in a certain spot on a certain day. But we'll do this middle option here, and then now we can identify the range that we're interested in. And remember, pardon? Did it? Oh yeah, the 10th. Let's go back more than a day. It was starting in 61, if I remember correctly. So let's go back to 1962, September 1st, 1962, through the 10th of September, apply. And so now here's a summary of our order. The period of record, the station ID. Okay. Continue. And you have to enter your email address after you specify a few things. These are going to enable or disable columns that come in that the resulting file. And so geographic location means that in every row it's going to have the latitude and longitude. These data flags are special just indicators that will point out if a certain day's precipitation was estimated, or if a certain day's precipitation is, like if there are statistical anomalies in the data, these data flags can identify. For the most part, airport stations like the Huntington Airport will have already had the data corrected such that there shouldn't be very many flags, but it's just going to create another column if we turn that on. And the only thing I'm interested in today is precipitation. And you'll notice here it distinguishes between precipitation and snow. And so precipitation here would be the overall precipitation, but then if temperatures are below zero and it's as snow, then it'll distinguish between those. And it's maybe also interesting to know the air temperature, so we could add that in. But if they're at the airport, they have a lot of different data flags available. So now we continue, and last thing, did we put in our email address yet? We'll do that. All right, submit order. All right, and you wait. Now, you know how students are. You're a student. Last time I taught this class, there were a handful of students who didn't start their assignment until the night before it was due. And for whatever reason, the website had a lot of jobs queued up, and they never got their data emailed to them for the homework assignment, the data that they needed to solve the homework assignment, until after the assignment was due. So even if you don't start the assignment until a little later, I'd encourage you to obtain the data that's mentioned in the assignment early enough that it'll get to you quick. Now, in our case, I think if I click check order status, it'll be available already, complete. Yeah, so it's available now, and I can download it. Open. All right, so here's that Excel file that every row is going to give the abbreviation for the station and the name, latitude, longitude. The elevation hasn't changed for any one of those. It's the same spot. The date, you'll notice it's day by day. And then here's the precipitation. This is the column that we're interested in. And these are the precipitation amounts in inches. All right? So you'll notice it's carrying the precipitation amount to the nearest hundredth. You can also specify millimeters. And if you do millimeters, I think it's to the value that's specified there is the 1/10 of a millimeter. One word of caution is that sometimes these headers, like the header descriptions, get offset from the actual columns of data. Sometimes there's a space there that isn't read correctly by Excel when it imports the table. So if you're looking at one of the columns and it's clearly latitude and longitude, but it's in the elevation column, then that probably means that there was an extra space somewhere as you were importing the data, and things got shifted over a little bit. All right, so this is the raw data. And remember what we said in the previous class, one of the ways that you can calculate an IDF table yourself is sort from highest to lowest. And so each one of these rows represents a day, right? So I'm going to insert here a numbered list where I'm going to scroll down all the way. And then if I go to the bottom, it'll tell me how many days of data I've got. All right, so I've got this many days of data. So my years of data is this divided by 365.25, which is how many days per year there are. The 0.25 is because there's a leap year, one extra day every fourth year. So I've got 55 years of data. So if I was making a ranked list, let me sort this from highest to lowest now. Sort largest to smallest. So the largest amount we've had in 55 years at the Huntington Airport, there was a day where in one day they had 3.89 inches of precipitation. So that's the 55-year storm, 24-hour total, that was actually observed. Now, by examining the rest of the data, they might say that actually the 50-year storm is even higher than this. Because remember, when we fit a curve, there can be lots of data points that cause that curve to be fit. And so the fact that any one data point is above or below the curve is going to affect the shape of it, but it doesn't necessarily mean that we're always going to have our curve fit the dots precisely. All right, so that's just sort of a glimpse of some of the things that you're going to need to do on the homework assignment. Those 3 sites will help you get started with that. Any questions on how to download the data or how to use the precipitation frequency data server? All right. A few years ago, I downloaded the data at the Huntington Airport and compared it to measurements I did at my house. I had a really nice precipitation logger at my house, and I was curious, on the days that it's raining at my house, is it also raining at the airport, and vice versa? And so what this figure showed is that over that time period, actually it was more rainy at the airport than it was at my house over that period. The red line is the Huntington Airport, and any time it jumps up means that there was rain, When it's flat, it means it was dry and there was no rain. And so there is spatial variation. You can have rain in one location and not in another, even when they're just 15 or 20 miles apart. So that's one thing to keep in mind, is that you can't extrapolate the exact conditions from one spot to another. This is kind of a quick proof of that. When you're measuring precipitation, these gauges need to be in open areas because of the effect of interception. Buildings and trees, vegetation can all shield from the effects of precipitation. And so the kind of rule of thumb is that you should be able to draw a 45-degree angle and see the open sky from wherever a rain gauge is placed. The other thing is that this diagram is showing the rain gauge close to the ground. Actually, the rain gauges need to be elevated up off the ground a bit because there can be splashing. During really hard rain events, the raindrop will hit the ground and bounce up and splash from the ground and can get up into the measurement pan. Getting accurate rain gauge measurements is pretty important, and there's some emphasis on keeping it away from the interference of both the surface and other objects that are near it. There are a couple of measurement techniques for aerial averaging, and look at this illustration, which is taken from your book. Let's say here's our watershed. Remember in the last class we opened up Google Earth and we panned around a certain ridge line, and we kind of got a sense for, based on the topography, where a basin was. So let's say that this line represents the ridge that defines a watershed, and we have some of our rain gauges are outside of there and some of them are inside. Well, the simplest thing you can do if you want to know what was the average precipitation depth inside of a watershed is just a simple average of the ones that are inside and the ones that are near it. So here we're including in the measurement ones that are near the watershed. So if we do an aerial average, 3.26 inches in this illustration. A more sophisticated approach would be to, in the Theissen method, break up the areas inside the watershed and say that you put greater influence on the areas that are close to a gauge depth of a certain amount. So, for instance, look at this Hyet gauge where there was a full 9 inches of precipitation. You draw a line between Hyet and Big Creek, and that's this dotted line here, and then perpendicular to that line is this big black one here, and it's the boundary between Hyet and Big Creek. And then you draw another dotted line between Foster and Hyet. So adjacent gauges have these connecting lines, and then halfway between them you draw a boundary. And so what you're trying to do is assign spheres of influence for each of the gauges. And so inside of the watershed, this is the sphere of influence for the Hyet gauge. And you'd measure the area of that subsegment of the watershed, and that's what this table is. It's a weighted average based on how much area is near the gauge, instead of weighting each of the gauges equally, which is what this did. This was saying each one of these gauges is important as the rest. But here, if we were to recognize the fact that this Hyet gauge is inside the watershed, whereas Crystal City isn't in the watershed, it should be counted as less. And so that contributing area for Crystal City is much lower, and since the depth was much lower for that gauge, the overall average becomes higher than it was in the previous simple average. The simple average, 3.26. If we assign the sub-areas, then it's 4.63 inches for the overall, because some of the gauges inside had higher depth. Does this approach make sense to you, the weighting? Okay, so here's another way of coming up with a spatial average. In the Theissen method, you just draw boundaries and you say everything inside of this zone gets 9.10. And I mean, that's better than a simple average, but we know that you're not going to instantly jump from having 1 inch of rainfall on the left of this line to 9 inches of rainfall on the right. And it's going to be more of a gradual transition than that. And so the Isohyetal method is an even more sophisticated approach that says, instead of having these spheres of influence, let's find out basically, if we can, these contour lines that shows what was the precipitation amount inside of the watershed. We know that here it was 9.10 and there it was 1.04, so there was probably a pretty steep gradient in the space between that. And so this line, this is 9, 8, 7, 6, 5, 4, well, maybe it's in increments of 2. It could be 2, 4, 6, 8. Well, I don't know what these increments are. The idea is that, okay, here's the 5, the 4, 3, 2. Yeah, 2.68 is between the 2 and the 3. So here, this is the 2-inch band. Here's the 3, 4, 5, 6. Then this must be, I don't know how we're going from 6 to 7 and then suddenly 9. I guess 9 is so isolated that maybe they're not drawing all of the contour lines for it. But what you would do is once you have a contour, you'd measure the area between the 5 and the 6. And so you'd have a depth, you'd assign it to the area between the contour lines. So the average between the 8 and the 6 is 7, and here's the overall area that had that band of precipitation amount. And now the average, when you do it this approach, is back down to 3.31, which ironically was pretty close to what we got when we just used this simple average. So that doesn't mean it's always going to be most accurate when you do an arithmetic mean as compared to the Theissen method, but these are just different ways that have been used over the years to come up with an areal average when you have point estimates for precipitation depth. You know, watersheds can be really large. You know, watersheds can be hundreds of square miles, and when you just have a handful of gauges, you have to have a scientific and defensible way for extrapolating how much rainfall there was over an area when you're starting with point estimates. And that's what these try to do, is you're trying to make it repeatable and defensible. So we've already looked at some maps of spatial distribution in the United States. Not only is there a variation in the amount, but as I'll show you in just a moment, there's a variation in the types of rainfalls that you see in different parts of the country. You know, we're more prone to the convective storms in the Midwest than they are in the coastal areas. We've already seen the precipitation map in Hawaii where they've got mountains and typical airflow patterns that causes the orographic lifting along the front face of those mountains. Temporal distribution and precipitation can vary over the seasons, and in coastal areas like in San Francisco, for example, you can see that they get very little precipitation during the summer, mostly during January, December, so it's clustered around the winter time. But that story is completely opposite in Midwestern places. Here in Chicago, Kansas City, you can see that the precipitation is much higher in the summer months than it is in the winter time. And it's because of the convective lifting that can cause storms more common in the Midwest than it is in coastal areas. Some places here in Boston, it's relatively even. They don't have a wet season versus a dry season. Here's another figure from your book that's showing the number of days with thunderstorms where the intensity is really high, the kind of peak storms that could potentially cause flooding. Now this isn't a percent, this is an average number of days, but thunderstorms are very uncommon in the coastal areas because they don't have as much convective lifting there. The precipitation is occurring maybe because of fronts approaching each other, but less so the really high intensity afternoon thunderstorms. Probable maximum precipitation looks at how much moisture could the atmosphere actually hold on to, and what's the elevation depth, you know, how high in the atmosphere, how tall could the cloud column be. If you look up into the sky, sometimes you can see the clouds are thin and it's just a small band of them. Sometimes they seem very deep, and if you're flying on an airplane, you may start to see clouds at 5,000 feet and not get out of them until 20,000 feet. And so you can, in your mind, think about the idea of a column and the depth of how thick are the clouds. So if you combine the amount of moisture that the air can hold on to and the duration of a storm, this is actually a figure that shows like record-breaking storm data, how long it lasted and how much rainfall was actually observed. And just coincidentally, when you put that on a log-log scale and you graph the location of those storms, this gives you a pretty clear idea of how big a storm could potentially be. So the probable maximum precipitation. So this, West Virginia isn't on any of these. We don't have any of the record-breaking storms here. But if we want to do a worst-case scenario, let's say that we're designing a dam and we want to have enough volume or enough capacity to release water from the dam, we want to say, like, what's the worst that could happen historically? If we had a really wet 30 days, what's the wettest that we could expect to see over the period of 30 days? Well, if we go to this figure, we could expect maybe to see 400 inches of rainfall. Now that happened in a very specific part of India where it's mountainous and really wet to the case that we probably wouldn't expect to see 400 inches. West Virginia on the usual annual basis gets 40 inches, and so this is 10 times as much rain as we usually see, and in 30 days instead of a year. But sometimes we do want to know the absolute worst that you could expect to see, and that's what this maximum precipitation figure kind of illustrates. I think it's really interesting. This is another way of expressing that same thing. This is more on a local basis, though, in the United States rather than on a worldwide basis. So if we're honing in on the precipitation patterns that we see here in the U.S., this maximum probable precipitation varies on the size of a watershed. And so the smaller a watershed size, the higher the maximum amount is going to be, because when you have spatial averaging, it's more difficult to maintain a really high intensity and a really high amount over a large area than over a small area. We've talked about that trend before. And this trend kind of shows the same thing. On the axis here, this is saying that it's the ratio of an area to a point. And so you can have high intensity at a single point, but not expect to see it over that same intensity over a large area. And so as the area size increases, then the percent of rainfall in that entire area as a representation relative to the point is going to get lower. So think about a watershed area. Here at our rain gauge, if we had 100 millimeters of rainfall in a day, what we're saying is, in this figure, if you had a watershed of 50 miles, you could only expect to see about 70% over that entire area of what you observed at a single point. It's not likely to be the same amount, 70% above or below. But now for the duration, you'll notice that the shorter the storm, the more variation there's going to be between the point and the area measurement. If you have a long storm, then the variation between a point and an area is less abrupt. It's up over 90%. So here are the principles here, that the longer the storm is, there's more averaging over area. And then if you have a smaller catchment area, there's less spatial variation. You can have, in a small watershed, everything can be the same, but in a big watershed, there's going to be a lot of variation within that watershed. Okay, we've already hinted at the fact that coastal areas have different precipitation patterns than in the Midwest. That's what this shaded map shows, is that in coastal areas, this figure is showing over time when the storm, when the precipitation actually accumulates. So on this figure, the steeper the line, that means a period of high intensity. So a type 1A, like they have in Washington and Oregon, it's kind of like a steady rainfall. There is a short period of higher intensity, but connecting 0 and 1.0, which is the percentage of rainfall, 100% of the rainfall in a 24-hour period, it's kind of more gradual. And there was a question on the concept inventory about this. People did relatively well on that question. talking about when is the storm the most intense. And so you can see here a type 2 storm is the one where it starts off slow, there's hardly any rainfall, but then suddenly there's this period where the line is really steep, meaning that there's a lot of rainfall accumulating all at once, and then it tapers off again. And so that's what we are. West Virginia experiences these type 2 storms where there can be periods of really high intensity. Now, type 3 is more on the East Coast and the Gulf area, more tropical storms dominating there, the worst case scenario. But for our purposes, the reason why you need to know that is there's a table here of the design storms and when you see it. Because we download the data from a rain gauge that says what was the storm during a 24-hour period, but if we want to do design, we want to convert that daily amount into a design storm that isn't just assuming that daily amount comes evenly during the whole day. And just because we have 5 inches of rain during a 24-hour period doesn't mean that every hour was 5 divided by 24 inches. So what we actually would do is if we had a certain amount of rainfall, 5 inches or so, you multiply it by that fraction, and then hour by hour, this is telling you how much of that fractional precipitation has occurred up to a point. So one of the questions you have in your homework, I think it's one of the book problems, you end up just multiplying the precipitation depth by this column of fractional amount, and then your time is over on the other axis. So we've got 24-hour design storms. Occasionally you'll design a system to analyze what happens during a 6-hour storm. And so it's the same idea. Over the course of 6 hours, what fraction of the precipitation is accumulated? And at the end, you're at 100% of the precipitation. So I've had students ask me, so does that mean like this is midnight, 0 is midnight, and then 24 is midnight again? It always rains at the 11 a.m., and that's not what it means. This just means when the storm begins, it is 0. And this is kind of like a typical pattern where you've averaged hundreds and thousands of storms together and tried to detect a trend line. There's going to be huge variation on either side of this, but this is the best fit line of the trend. There are differences that vary based on region. Okay. Oops. What'd I do? All right. Another one of the problems that you have in the book is looking up precipitation data off of a map. And so these maps are similar to what you're getting with the Precipitation Frequency Data Server, where you pick a point, and with the contour lines, here it's showing the 2-year, 60-minute precipitation. There are figures like this in your book based on the statistical analysis of the precipitation amounts. And once you look up the 2-year and you look up the 100-year, then you can use those values that you get off of a figure and extrapolate. If you know the 10-minute and the 30-minute storm, no, I'm sorry, if you know the 5 and the 15, you can get the 10-minute in between. If you know the 15-minute storm duration and the 60, you can from that do kind of like a weighted average and get the 30 minutes precipitation depth. In a similar way, you can extrapolate the return period. If you know the 2 and the 100, then you can get the 5-year storm, the 10-year storm, the 25, and the 50, just by using these coefficients and plugging them into this equation. So you can just look up the 2 and the 100-year storm out of the tables, and then from that find the 5-year storm, the 10, 25, and 50. It's a way of just kind of estimating between the two extremes. I'd want to drive home the point, the difference between precipitation depth and precipitation volume. Because when you're looking at precipitation data, it's going to express it most often in terms of a length. So either inches of precipitation or millimeters of precipitation. And the way that you would convert that into a precipitation amount is you'd have to multiply it, that depth, by the area over which it's falling. And so just think about the units. A volume would come by depth multiplied by area. And when it comes to intensity, you would have to divide the precipitation amount by the time over which it's falling to turn it into an intensity. And the trend with the recurrence interval is that the high intensity storms are rare. They have a lower probability of happening in any given year. And so we talk about a storm size by how infrequently we observe it. The 100-year storm, or sometimes people have referred to like the perfect storm. There's even a movie that talks about the perfect storm, about a fishing boat that sank off the coast of New England. And in that case, I think it was 3 separate 100-year storms that converged on a single location was the perfect storm. We're going to skip over these 2 slides. All right, so here is a pop quiz. Here's an intensity, duration, frequency table. Are these depths or intensities that you're seeing? How do you know it's depths rather than intensities? Right. As you're going down, the amount is increasing. So now, I guess they've got it represented so that the years are on the rows and the times are along the top as columns. But let's say 5-minute to 10-minute storm, what we know is if it was intensity, the intensity would be decreasing because it's the shorter duration storm that has the highest intensity. So even before we look at the label on this, it is a, I guess I could remove that, right? The answer is maybe inches. And so that's a depth. That's a depth. And the way we know it is just the fact that the amounts are getting larger rather than decreasing. All right. We've talked about why there's more rain in this location. I already spilled the beans on that one. All right, so that's all I have for you today. Let's refresh our memory of the announcements here. The homework assignment's due on Thursday, and I've also promised you a quiz on that day. I gave you back the last quiz in class on Tuesday, right? All right. So any questions? All right, have a good day.